Arguably the most famous unsolved problem in computer science. And actually, if you're cracked enough to solve it, the Clay Mathematics Institute will literally give you $1 million. And all you have to do is come up with a proof for this philosophical question. If you can verify a solution quickly, can you also find the solution quickly? Or in other words, is handcrafting a beautiful meme just as easy as admiring its beauty? To me, the answer seems obvious. Of course, P does not equal NP. Many others believe this, but nobody's been able to prove it. I arrogantly set out to prove that P doesn't equal NP myself and couldn't do it. What's scary though is that if everybody turns out to be wrong and somebody proves that P does actually equal NP, then every password, encryption key, and crypto wallet becomes instantly crackable, while simultaneously curing cancer and ending world hunger. It would be total chaos. In today's video, we'll look at the weird, mind-bending math behind the greatest unsolved problem in computer science, and try to win $1 million in the process. The P versus NP problem was officially defined in 1971 by Stephen Cook in his famous The Complexity of Theorem-Proving Procedures paper. But we can actually go back even further to 1955 when mathematician John Nash warned the National Security Agency that for well-defined cryptography, the effort needed to break a code doesn't scale linear. It explodes exponentially as the key gets longer. He was implying that P does not equal NP, but what's crazy is that there are thousands of papers, decades of research, and zero proof either way. But to understand why it's so hard to prove, we first need to understand the math behind it. P stands for polynomial time, which are problems a computer can solve efficiently even as the input gets bigger. Think about an algorithm that sorts a list of names. As the list gets bigger, it takes longer to sort, but at a deterministic and reasonable pace. When sorting a list of names alphabetically, the amount of work on the CPU is roughly proportional to n or n log n. So if the list gets 10 times bigger, the computer does about 10 to 20 times more work. And problems that grow at a reasonable pace like this are called P. But then things start to get weird when we talk about NP, which stands for non-deterministic polynomial time. These are problems where you might be able to check a solution quickly, but finding it, good luck. Some examples are the traveling salesman problem, Sudoku puzzles, or scheduling your dev team's vacation days. If you already know the answer, verifying it only takes polynomial time, but if you need to find the solution from scratch, you might be waiting until the heat death of the universe. For example, imagine I give you two prime numbers, 7 and 13, then ask you to multiply them together. That's a piece of cake that you could likely do in your head right now. But now imagine this problem reversed. I give you 91 and ask you to find two prime numbers to produce it. You might need to test out a few different possibilities, but you can still do it in your head. But now try the same exercise on 69, 420. What you'll find is that it's far more difficult because you need to explore all kinds of different potential options. And that simple fact is why prime numbers are the foundation for modern public key cryptography like RSA encryption. Multiplying two primes is easy, but factoring back to the original components is extremely hard. What's funny is that we know it's hard, but mathematicians can't actually prove that it's hard, and can't prove that no faster algorithm exists. Another classic problem like this that you might see on a technical interview is the traveling salesman problem. You have n cities, and you want the shortest route that visits each one once. The brute force approach is to try every possible path, and that gives you a lot of possibilities. n-1 bang factorial. For just 15 cities, that gives us like 87 billion different possibilities. That'll make your CPU explode, but here's the twist. If someone hands you the optimal route, you can quickly verify it by checking if it's shorter than the alternatives you already know. Verification is easy, discovery is brutal. Because of that, algorithms in the real world have to be optimized for different rules, or heuristics if you want to sound smart, which aren't guaranteed to get you the best answer, but they should get you pretty close. Basically, you have to trade the optimal solution for a reasonable compute time. So at this point, we know that a problem is NP if a solution can be verified in polynomial time. But there's another special group of problems called NP-complete, and these are the worst of the worst. If you can solve any one of them in polynomial time, you can solve all of them in polynomial time. The first NP-complete problem was SAT, the Boolean satisfiability problem. Imagine you have a giant logical expression that looks like this. Is there some assignment of true-false values that makes the whole thing true? Checking the answer is trivial, but finding the answer requires tons of different combinations. What's interesting about this one though is that it was the first problem to be defined as NP-complete by Stephen Cook in 1971. Since then, many other problems have joined the club, like traveling salesman, Sudoku, circuit design, protein folding, and a bunch of other problems that are really important to humans. What's really weird though is that they all simulate each other in terms of complexity. complexity. And that means if somebody finds a polynomial solution to solving one of them, then all of them will be solved instantly. Hypothetically, if somebody did that, p would equal np, and the world would completely change overnight. The things that were once impossibly hard are now trivial. But despite 50 years of trying, nobody has been able to find a fast algorithm for any NP-complete problem. In addition, mathematicians have tried to end this debate with a variety of different proof methods, but every time they hit barriers that make it impossible. But why is this problem so important, and why did I even bother to make a video about it? If you really take a minute to think about it, the implications are kind of mind-blowing. If p equals np, then every puzzle has a shortcut, and the universe is ultimately efficient, like a machine built by an intelligent designer who never wastes computation. But if p does not equal np, then reality itself contains problems that can't be cut short, like the universe runs on deep computational limits, the kind you might expect if you were living in a simulation trying to conserve processing power. But the scariest possibility isn't that p equals np or that it doesn't, it's that God or the universe or the simulation already knows the answer, and the entire purpose of our existence is to be the algorithm that computes it.
Let me out! Let me out! I want out!
Unfortunately though, after several minutes of prompting, I still haven't solved.
Okay. Well, we have like 9 people. Okay. Let me send the link again. And for the video, it's basically saying, well, most of the encryption done is using RSA encryption. And it's basically a type of way to encrypt our messages or like our passwords and stuff. And basically, it's pretty hard to find or compute these passwords and trying to hack into things. But it's basically saying if we find the polynomial time or something that we can find in O of n, so checking each and everything in the list once or something like that, then basically it would be crazy because we could potentially hack into all these computers using O of n, which would be easy using like GPUs and stuff like that. Anyways, I believe Jordan is here for the first time. So, Jordan, you're going to want to go to this link, the GitHub link, as well as install Git, which would be shown in the class the website. Let me actually share my screen. Okay. Basically, it'll be right here. How to clone a GitHub repository. You're going to want to install Git and basically follow the steps on the GitHub website to basically clone using HTTPS. Oh yeah, just so you guys know, S in HTTPS means secure. So this one uses things like RSA encryption and TCP connections. Anyways, yeah. And then what else? Right. Last week we were, no, not last week. Jordan. Got it. Thanks. Okay. And Jordan, have you used Git before, or do you know what it is? No. Okay. It's basically just kind of a way for us to share code as well as keep track of your code on a non-local computer. And you'll use it a lot once you get into the field. And like, yeah, you'll get more information in this link, I believe, Git. Anyways, last week we were working with, not last week, 6 weeks ago-ish, we were working with auto prepare cats and dogs. So this, let me share my code. So we're basically working with Oh my. Okay. We're basically making a cats and dogs classifier. So basically, we have three files. One is auto prepare cats and dogs. So we get the pictures of cats and dogs from the Kaggle website. We extract it using auto prepare cats and dogs. Later, you'll see it split into two folders. This is what we're doing in this file. We're basically getting the zip file, extracting it, separating it into cats folder and a dogs folder so that we can come to the neural network and basically use those two folders to train our AI using the cats images as well as the dogs images and building a neural network that will train on these images and be able to predict using an image. It gets the image, uses the neural network that we trained, and basically passes our image through the neural network or the model that we created using the neural network. And it will classify and say like it is 99% a dog or 2% uh yeah. And I believe we didn't do binary neural network yet. We didn't do binary predict yet, but we have done auto prepare cats and dogs. So basically, we download the data set of Kaggle, we unzip it, we create the clean folders, so the cats folder and the dogs folder. We find the image folders. So basically, when we create those folders, we want to know the exact location, something called a PWD. And that's basically the directory link string indicating the directory. And then we want to copy a limited number of images off of Kaggle or that zip folder into our folders. And then here we want to make our clean up temporary files as well as orchestrate the whole pipeline. Functions. And what else do we need to talk about? Okay, for Jordan, I guess. So where you have the code folder, which is basically just the code of previous weeks. If you want to go dig through them, you can. And usually when you guys open up or look at a project, you guys are gonna wanna look at the README. So README basically, as the name suggests, it's a README. So you're just gonna want to read it for documentation or seeing how to run it. And then we have the code folder. We have the solutions folder. So basically solution for each week. And yeah, that's the main two things you want to know. We're on week 8. Okay. Last class, I believe we said Adam went, Albert went, Kate and Charlie went. Okay. Liam, do you mind sharing your screen whenever you're ready? And then next will be James. And the link is in the chat for the live share. Or you guys can just download it off or get it off Git as well. Liam, whenever you're ready, you can share your screen. Okay. I don't know if he's there. Okay. Oh, Elisha is weird. Then can you download the code off or get the code off Git or GitHub? You can go next. So during that time, just get it off Git or GitHub. And James, can you share your screen when you're ready? Okay. Can you try joining again? I don't see the request. Okay. I think that was you. Is that Shrek? Oh, sharing perm. Zoom changed their layout. I have no idea where. Yeah. Okay, I found it. Okay, you can probably share now. Oh, okay. Where were we? Cleanup. Okay, this is gonna be easy. Just let's go step two. Remove the zip folder. So you're gonna just check if there's a zip folders first. So do if os.path.exists, and then inside the bracket, because it's a folder, I mean function, and then you do all caps zip underscore name colon os.remove zip name. And yeah, next, number three, if os.path.exists, extract folder, then you want to remove it. Step four, you don't really need to do step four. That one was easy. Let's do the next one. Okay. Delete the pass. I mean, it doesn't really matter actually. I didn't even know that. Okay. Step one, download the dataset. So do download dataset, call the function. You guys might have forgot, but we made that function 6 weeks ago or something. Nothing to pass in. If you look at open the bracket again. Um, okay, yeah. Then it says, the bracket says nothing in there, right? So it's just circle, circle. The arrow means what it returns. So it just means that it returns nothing. And inside the bracket, there's nothing. So that's what you see when there's like no argument to be passed. Step two, unzip dataset is the function that we call. And then create clean folders is the next one. So we're basically just creating a function that gets called when we run this Python script. And yeah, cat source, comma, dog source equals find image folders, comma. Yep. So for those who don't know, create clean folder, create Q. And that's a function. And yeah, we don't pass anything to it. So those of you that don't know, create clean folders passes out two values, and we can assign that using the comma. So we're basically assigning cat source to the first return value and dog source to the second. And then we have step 5. We want to copy the limited images. So do copy limited images. First one, we do bracket and then cat source. Delete. I meant the circle bracket, but yeah, cat source, cats folder, comma max images per class. And then just copy that line and then change it to dogs. Good job. And then call cleanup. And that should be it. And yeah, you can stop sharing. And yeah, I believe I didn't give permission for you guys to run it first. Anyways, if you guys want to run it, I believe this is done. You guys can try running it. Let's see, where's my terminal? Okay. Can you guys see my screen? Like, read it? Yeah. Almost. Maybe this is good. Anyways, so let's just do this. Python, we have Kaggle command. Oh, pip3 install Kaggle. Essential. Okay. And now we have raw data set. We have the cats and dogs. Now, what does it say? So we downloaded the zip file. And then we have an error in 182, which is create clean folders. Okay, it's saying that we already had affixes and we already had a cats folder. Oh, I see. 16. Oh, there was a repeat. Okay, now let's try it again. Now what's the next error? Why do we have a repeat here? Oh, we have the wrong function here. Find image folders. Now what do we have? Clean up. No, we don't want to. Okay, now it should be. Okay, so we have the dogs folder and the cats folder, and we don't really need this. Delete. Okay, next, let me sure to get. Next, we'll do binary neural network. So what we have to do is load the images that we have here, the cats and the dogs. Okay, let me delete these. Okay, delete. Oh, we already did it. Okay, so we load the images, we initialize the parameters, we create our activation functions, so ReLU and sigmoid. We have our forward propagation, as well as our compute loss and our backward propagation, as well as our update parameters and train model. Did we already do this? Why did I code here? Okay, we'll do that, and then we'll move on to binary predict, which is when we load our model that gets trained here, our ReLU function, as well as our sigmoid function again, as well as propagation, preprocess image, and the main function. So I'm gonna need you to open up the binary neural network file. Now, Liam, if you can try it again, are you able to share your screen or? Let me know. Okay. Now we can do initialize parameters. Should be all the way at the top around, like second function from the top. Yeah, that one. And let me open up my initialize parameters. Okay. So first, we're gonna set a random generator. So go to 114 tab, one tab, yep. And then we'll do RNG, so randomness equals np.random.default RNG, uh, default RNG as in default underscore RNG. Yep. And then that's a function. And then we set the seed parameter to equal to 42. So we do seed equals 42. Why does it not show you the parameters for the RAM? Oh, maybe because you don't have a Python environment. Anyways, RNG, and then we do weight one, so W1 equals RNG.normal. Bracket is a function. We pass in 0, comma 0.01, comma size equals 0, comma 0.01. No, for the first parameter. Sorry, I meant the first parameter is 0, and then the second parameter is 0.01. Yep. Uh, Comma, and then size is equal to circle bracket, input size, input underscore size. So these are the parameters that we get from the initialize parameters function. So the input underscore size, comma, hidden underscore size. Yeah. Next, we do B1. So we do B1 equals np dot zeros. Yeah, zeros, circle bracket, so double circle bracket. So we're passing in a tuple of 1 comma hidden underscore size. Yeah. And the next is W2 equals, and then you can just, actually, let's just copy line 115 and 116 and then paste it. Wait, how did you do that? Why did it copy your 2 lines, but not copy your B1? That is the weirdest thing I've seen. Yep, B2 equals. So for the W2, it should be RNG.normal. The size should be different. It should be hidden size, comma, 1. No, like inside the bracket, So delete the input size. Why is your code not showing on? Can you save it? Control S. That's weird. Okay, whatever. Doesn't matter. Hidden size, comma, 1. And for the B1, B2, it should be 1, comma, 1. So as you can see, we're basically building. You don't know much about matrices, but okay. Let's just think of it as there's one input or input size amount of inputs, and we have a second layer, which is the hidden size. So we have to match the W2 to have the same hidden size input as whatever the output for W1 is. And then W2's output should be 1, as in we should get a binary yes or a no. Next, we want to return that. So return, and this should be a hash map. So a dictionary. So that's the curly bracket. Yep. Inside the curly bracket. Do you guys know what a hash map is? Or a dictionary? Or do you know? Have you seen it before? Oh, you can just type it in the code. No. Okay. Hash map or dictionary is basically like a key value pair. So you're basically gonna have, okay, how am I gonna show you it? Oh, I think, oh, you downloaded it. Okay, that makes sense. So in the chat, I'll say it in the chat. Basically, a hash map is a key value pair. So the key is the first value of whatever gets mapped. So like key one is mapped to two. We have like key two, something like this. And key one is something called a key, while two is something called a value. And basically, when you search up something in a hash map, you get its value in all of one time. You guys just looked at this in today's YouTube video, right? There's something called a big O notation, and it's basically the complexities of whatever algorithm that you're making. So one for loop going through a list is O of n because you actually take n max amount n times to check if an element is in a list. Whereas if you do two for loops, so recursive, anyways, two for loops, so for I in range, for j in range, then that would be O of n squared because you're checking it twice, right? But in dictionaries, what's awesome about them is that you can actually just check in O of one. So even if you have like 100 different keys, then you can just search up one thing and it will give you it in O of one time. Anyways, return a hash map, and the first key will be W1, all caps. So it's a string. Yep. And it's mapped to a value W1, non-string. Yep. W1, comma, and then B2, I mean B1, same way. B1, W2, B2. Yeah. And then do that for all of them. When you guys pursue computer science and do interviews, most of you, okay, I don't know how it's going to change with AI, but most of you will be doing leak code and technical problems. Hash maps will be when you guys use it the most in interviews because of its all of one time. But yeah, if you guys ever want to try kind of testing your limits on coding, you guys should try out me code or leak code. And yeah, that's it. Liam, you can stop sharing. I think Nicholas did. Okay. Nicholas, can you share your screen? And we will do
Me?
Liam. I mean Nicholas. Nicholas. Nicholas, we will do forward propagation. Yeah, forward propagation. Whenever you're ready.
Which one?
Forward propagation function inside the binary neural network .py.
Where?
So binary underscore NN. So the third file in that. Yep. You can just copy it or you can download it, up to you. It should be on the right. Or technically you can also edit it on GitHub, but or
No.
oh, it's read only. Okay.
Yeah.
Yeah, just copy and paste, I guess.
Are you able to like make a share session or?
Oh yeah. Here, I'll send it in the chat. I don't know. Do you guys like the share session? I know that it sometimes lags a lot
Yeah, it's
and it
not
moves
easy.
around a lot. I don't know, up to you guys. You guys can either copy it or every week or download it every week, do the share session, or the best way is just using Git and just doing Git pull. I'm not sure what you guys like the most, but Git is the one that you guys will use the most in work or projects and stuff like that. But even outside of this class, you guys should be doing projects and uploading it to GitHub just to get better. Should be down a bit. Down one more function. Yeah, forward propagation. So this is basically you're gonna do a dot products and matrix multiplications. So just do step one. We'll go from there. Basically, what we're gonna do is we're getting the parameters, so just unpack them. So we'll do W1, go to, yeah, just do W1, comma, B1, comma, W2, comma, B2, comma,
Okay.
equals W2. So the weight 2, comma, B2 equals parameters, so whatever we get. And parameters is gonna be dictionary. So we're gonna do to access the dictionary key or value, get a value, you do a bracket, square bracket. And we insert the key, which is quotation W1, all cap. Yeah, one. Yeah. Oh, one more thing. Before parameters, put a circle bracket. So it should be like this. And then, oh, what happened? Anyways, and then,
You just keep deleting it.
oh, okay, I think it's lagging or something.
There we go.
Anyways, yeah, just do it without it at this point. Just do comma. Imagine that there's a tuple and we're unpacking the values. So we do comma, parameters, W2. I mean, B1. And then just continue for W2 and B2. Yeah. Yeah. And basically what I mean by tuple is it's like unpacking the values like this. So that the first value gets, so W1 gets parameters W1, and B1 gets parameters B1. And next, we're going to do X1,
Inside or outside?
next line. Why is it going up? Oh my God.
Maybe because
Enter.
you're moving your mouse.
The thing is, I'm not even on that screen.
Here?
Yeah.
Yeah, that's you.
Oh, maybe my pointer is just stuck there. Okay, I'll move it. It's because I can't even see the zoom when I do that. Do Z1. No circle break. Z1 equals X, capital X. So this is from the parameter that we were given for propagation, and we get two parameters. X ampersand. Oh, what's that? At sign. What's that?
This one?
Mm, whatever you call this. The at sign. And
Yeah.
W1 plus B1. So basically what we're doing is it's a neural network. We're basically doing dot product of the weights onto the X. So a dot product is something in linear algebra. I don't think you guys will know it yet. Just imagine it as two matrices multiplying against each other to get a newer value to change the weights. And we're adding B1, which is called a bias vector. So we're basically just a parameter that tries to remove bias in a way. This is kind of too advanced topic for you guys, but I don't know. Just imagine it as something that you need to change the weights in a way that works. Enter A1 equals A1 equals ReLU, so ReLU, no B. Yeah. And we pass in Z1. And then next one is Z2 equals A1. Or maybe it's the other people in the slide share that's. Let me try and kick.
Wait, you missed this one. And this.
Maybe I have to scroll down. No? Okay, anyways. A1 at W2 plus B plus B2. Enter A2 equals sigmoid, and we pass in Z2.
A2 equals what?
Sigmoid, so SIGMOID. And inside it, we pass that's a function, we pass in Z2.
V?
Z, the previous variable that we made. Z, zebra, Z. Yeah. And then we make a cache or a hash map again. Let's just do return A2. No need for a tuple when you do return. Just do a space here. Comma, dictionary. So curly bracket, or you can do dict. Let's try dict. Dict, and that's a function. Yep. And then we do actually I'll can we do dict? You know, scrap the dict. I don't know how to do the dict. Curly bracket instead of the circle bracket. And the first key is Z1, string Z1, all cap. I'm just gonna remove this. Yep. And then you're gonna do the value for the first key is Z1. So inside the curly bracket after the first string, yeah, colon, Z1 before that. I mean, after the colon. Z1, yeah, comma. Now we repeat that pattern for A1. No curly bracket. Yep, yeah. A1, colon, A2, and A1, and then Z2, Z2, and then A2, A2. Yeah. So when you guys for loop through dictionaries, actually, never mind. Scrap that. And yeah, that's it for you. So you can just Control S, save it, and exit. Okay. Now that we did that, what else do we have? We did the program. The train model now. Okay, Jordan, are you able to share your screen? Or did you access the live share? Um, and also before that, maybe I should share. So, Jordan, as well as other people who don't have Git yet, once you guys download Git and once you guys make a GitHub account, all you have to do is go to code. If you have a Git downloaded, you can use Git clone this. Or if you don't, you can also do Git clone this. SSH is usually better, more security, as more security than the HTTPS. And basically, yeah, that's all I wanted to share. Jordan, are you able to share your screen or able to access SlideShare? Okay, I guess not. Then we'll go back to Adam. If you can share your screen, we'll get started with train model.
Okay.
And yeah, you can share it whenever you're ready. And do you guys do any coding outside of this class? So on other topics that are not related to Python AIML? Or do you guys only try to do, okay, Java? That's cool. And do you like Java better or Python better? You don't have any, all right. Most of you are in middle school. Yeah, Python is much easier to understand. Adam, on the bottom right, just click continue as anonymous. Yeah, I have tried Java, but I don't like it. But it's up to how people
Yeah.
feel. Yeah, one second. I don't really see it. Hmm. Okay, I see it. No, it should work. Yeah, Java has a lot of object-oriented programming, so it's good to learn, especially since, I mean, real coding comes from object-oriented programming. Yeah, the semicolon on every line comes from C++ and C as well. You should get used to it. Okay, so step one, we want to initialize the parameters. So we're gonna do train model. So to initialize the parameters, just do parameters equals delete the pass or whatever. Up to you. And then do parameters equals initialize parameters. So it's that function, so you can just enter. Yep. And then that's a function, so you do bracket. Yeah. After the initialize parameters. Why does it move like that? Inside the bracket, you want to do input size and hidden size. Yeah. Comma, hidden size. Yep. Enter. And then you want to do for each for epoch in range of epochs. So range function. So you have to do no epoch, no of. So delete the of. Range is a function which creates a list of numbers, and the number range that we want is epoch amount. So that's why we do range of epochs. And then we do colon at the end because it's a for loop. And then we do enter and we do y underscore prediction. So y underscore pred, or yeah, prediction, comma, cache or hash map or dictionary or whatever you want to name it. Cache as in CACHE. Do you guys know what a cache is? Actually, you guys probably don't. Caches are mostly used in CPUs. CPUs are basically what's in your laptops or computers or data centers. Basically, it creates a local memory that is faster to access than memory on RAM itself or storage. So like SSDs or hard drives. And yeah, basically you just want a cache because you want to access some code or memories faster than others or more frequently than others. So rather than reading off of memory itself, you can just read off cache. Yeah, cache data. Where are we? Yeah, cache equals forward propagation, which is a function. Forward propagation. Yep. Underscore. Remember that code should be like one word each, like variable. Think of it as variables. Forward propagation, and that's a function. And we pass in the first parameter, x underscore train. So these are from the train model arguments, and x train is capital X. So you can just press enter. Never mind. You have to change it to capital X. Yep, comma, parameters. Yep, enter. Loss equals compute loss, compute underscore loss, bracket, y underscore train, y underscore prediction. Yep. So in that loop, first we did the forward propagation, then we did the computing the loss. Now we want to backward propagate. So enter. Gradients or grads equals backward propagation. And we pass in x underscore train, y underscore train, comma, parameters, comma, cache. Next, we want to update it. So update our parameters. So do parameters equals update parameters. Update parameters should be one word, function. Yep. Bracket parameters, comma, grads as gradients, comma, learning rate. So basically, whenever you guys train neural networks or models like this, it'll feel repetitive, but you guys are actually doing like, it should be like the same thing, right? You're just creating a forward propagation, you're creating the compute loss, you're just tinkering the values a bit. And yeah, enter. If, holy, it jumps around so much. Verbose, space, verbose, which is a, yeah, if verbose. So verbose is an argument that gets passed in, and tuple, so circle bracket, yeah, yeah. Inside it, you do epoch, modulo. Do you guys know what that is? So it's percent. Uh, it's epoch and then percent sign. Yeah, percent sign, what it does is it's called a modulo, and it basically gets the remainder. No, the modulo is the percent. Yeah, and then you do 10. So it's basically saying, yeah, and then do equals equals 0. So it's basically saying if epoch divided by 10 and the remainder is 0, then do whatever that makes sense. And then do or epoch equals epochs minus 1. Remember that equals equals since it's conditional check. Yep. And then do colon for if, then print, and then I'll just, since it's useless, and then we just want to return the parameters. So we're basically just giving an update on the epoch status. We're going to want to return it after the for loop. Return the parameters. Yeah. And yeah, that's good. You can stop sharing. Is it like cookies? Yeah, since kinda, yeah. You can think of it as cookies. Although cache itself is a different story for CPUs. Like hardware cache and software cache is different in a way. Learning rate. And this one's pretty self-explanatory. Anyways, I actually wanted to show you guys. Maybe we can quickly run through a hash map. Okay, so you guys get that hash maps are key value pairs, and there's a famous problem called two-sum. Seven. And a space, actually, we don't really need this. Anyways, so what we did today, we did the auto-prepared cats and dogs. You guys can see the solutions for that. And basically when we run it, let me open my terminal. Yeah, it downloads the dataset from Kaggle. We extract it, unzip it, and then you'll see it here. Oh, dogs, cats, and then we build our neural network. So we built our forward propagation. Actually, I believe we're building that next week. Yeah. We have our compute loss, backward propagation, and then in train model, we just call those functions. And then if we call this, No module sklearn. Install it. Okay. Cool. Then it'll stop for a bit since it's training. And after a while, we should be getting something. Yep. Now it's showing us at each epoch, our compute loss function shows that at first it was 69, now it's 39, which means the loss is getting lower, which is a good sign. We're doing 99 epochs. The test accuracy is 64%, which is, I mean, pretty bad in my opinion. But we can't really train that well with what, 70 images on our CPU. And what, we only trained for like 1 minute. Usually you want to do like thousands of runs, right? Using a GPU. Anyways, now we'll do a Blicket. Does anyone have any questions before that, though? And yeah, I encourage you guys to try out other languages other than Python, since Python is really just the easiest one. I mean, the next step that people usually go towards is C and C++. That's what you guys learn in school, university as well. Don't try C sharp. Okay. Uh, if C sharp is hard, you guys won't like C or C++ as well. Just because these languages are, you're gonna have to do memory management, and it won't really, you guys won't really see a lot of results. Say, for example, you build a project using C or C++, you guys won't be able to see like nice UI like you guys do for Python, right? On the other end, if you guys know it well, you guys will realize that it's just way better than Python. And in terms of JavaScript, JavaScript is just a language for the websites. It's not really good. I mean, some people like it. Anyways, let's just do duplicate. Let me share my screen. Link is in chat. And in terms of the projects that we do, have you guys been trying? Session has expired. Please log in. Okay. Have you guys been trying out these further project recommendations? These are pretty, I mean, you guys are getting into topics that we don't typically learn in this class, right? Because this class is only for Python AI ML, which is a pretty, I mean, one of the ideas that we can go off of, right? I mean, you guys can try building out front-end websites and trying out things like this. But if you guys ever get stuck while doing that, please let me know. If you guys want any help as well, you guys can email me. But yeah, okay, all good. Let's get like 1 or 2 more minutes for people to join. Can't run it right now. Okay. All good. I'll start the recording as well.